Hi, I want to talk about the rate at which energy is expended by the human body through the process of radiation. Now, any object above absolute zero is emitting power, and the rate at which we emit power is equal to the emissivity of an object times the Stefan-Boltzmann constant, which is 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the fourth power, times the surface area of an object, times the surface temperature of the object to the fourth power. Now, objects that are in environments above absolute zero also absorb energy. And the rate at which they absorb energy is going to be the emissivity, because emitting and absorbing are just the same process in opposite directions, times the same Stefan-Boltzmann constant, times the same active surface area, times the temperature of the environment to the fourth power. Now, if you're talking about something like a star, where the temperature of deep space is about 3 Kelvin, a star's surface is typically in the thousands of Kelvin or more, you normally don't worry about the environment. But when you're talking about humans, usually the difference in temperature between our skin and our surroundings isn't that great of a difference. But even though the temperature may be relatively close, when you take that temperature to the fourth power and then compare it, you can end up getting pretty big differences. Now, human beings, regardless of what our skin tone and complexion looks like, are really good at emitting and absorbing energy. Our emissivity is about 97% or 0.97. And a human being will have a surface area of around 1.8 meters squared. Now, our surface tension is our surface temperature is usually a little bit lower than our core temperature. So the core temperature of a human under normal conditions is usually around 37 Celsius, about 98.5 Fahrenheit. Well, our surface temperature usually ranges somewhere between the low 30s in Celsius to about 34. You get up to like 35, 36 of surface temperature. Did it again. At that higher surface temperature, you're starting to run into the point where your internal temperature is really dipping into the feverish range. So let's say that the person going swimming has a surface temperature of 34 Celsius and they jump into a 72 Fahrenheit swimming pool. What is the net rate at which they are emitting energy? So, with radiation, we absolutely, positively have to work in the absolute temperature scale. We have to convert everything over into Kelvin. So Celsius to Kelvin is pretty easy. I add 273 Kelvin, and my 34 Celsius becomes 307 Kelvin, because the only difference between the Kelvin and Celsius scale is the starting point. Now, Fahrenheit to Kelvin needs to take a pit stop at Celsius land. So the first thing we do to convert from Fahrenheit to Celsius, we subtract 32. So 72 Fahrenheit is 40 Fahrenheit above freezing water. Now 40 Fahrenheit, they're 5 Celsius for every 9 Fahrenheit, and 200 ninths is about 22 Celsius. So I add 273 to 22 Celsius, and I get 295 Kelvin. So, what would feel like a comfortable to slightly coolish swimming pool is about 12 Kelvin in temperature difference from your skin temperature when you jump in. But if I take those temperatures to the fourth power, 307 to the fourth power gives me 8.883 times 10 to the 9 Kelvin to the fourth power. And 295 to the fourth power is only 7.573 times 10 to the 9 Kelvin to the fourth power. So the difference of temperatures to the fourth power is going to give me 1.31 times 10 to the 9 Kelvin to the fourth power. Remember, I'm not taking 12 to the fourth power, I'm taking the temperatures to the fourth power and then doing the subtraction. So, if I plug everything into my power equation, my emissivity is 0.97 times 5.67 times 10 to the negative 8 watt per meter squared Kelvin to the fourth power times the surface area I mentioned of 1.8 meters squared times 1.31 times 10 to the 9 Kelvin to the fourth power. I get a net power of about 130 watts. Now, if you were to sustain this net energy output with your surface temperature remaining the same and the pool temperature remaining the same, that would be generating about 11 million joules of energy over the course of a day, which in terms of dietary energy would be about 2,700 dietary calories worth of energy that you're emitting. So the energy that we need to take in isn't usually to allow us to do mechanical work like lifting something. That energy is largely about maintaining our metabolic temperature, trying to make sure that we can keep our core temperatures within normal parameters and maintain that cellular respiration, cellular energy that's going on that cellular level. Thanks for watching.